Hello there, and welcome to the Science for Sleep channel. Tonight, we'll explore the elements of the periodic table that have existed since moments after the Big Bang. Carbon forged in dying stars now forms your bones. Gold, created in colliding neutron stars, rests in rings and jewelry, and hydrogen born in the universe's first seconds fills the space between galaxies. These quiet wonders have witnessed millennia pass, holding secrets we're only beginning to understand here on Earth. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if gravity itself has softened. Just before we begin, if this helps you rest, consider liking and subscribing. One sleepy soul at a time. Now, let's begin with the elements. Hydrogen makes up about 75% of all normal matter in the universe and was born just seconds after the Big Bang occurred. This simple element, with only one proton and one electron, came into existence when the universe was still unimaginably hot and dense. As space expanded and cooled, hydrogen atoms formed from the energy that filled the cosmos. Every star you see in the night sky burns hydrogen at its core, fusing these atoms together to create light and heat. The sun converts millions of tons of hydrogen into helium every single second through nuclear fusion. Without hydrogen, there would be no stars, no light, no warmth spreading through the cold vastness of space. This element connects us to the very beginning of time itself, reminding us that we live in a universe still shaped by those first moments. Hydrogen drifts between galaxies, patient and eternal, waiting to be drawn into new stars that have not yet been born. Gold in your jewelry was created in the violent collision of two neutron stars billions of years ago, somewhere far across the galaxy. These collisions happen when two incredibly dense stellar remnants spiral into each other at nearly the speed of light. The impact releases more energy in a few seconds than the sun will produce in its entire lifetime. In that brief moment of unimaginable heat and pressure, atomic nuclei smash together to form heavy elements like gold, platinum, and uranium. The gold then scattered into space as dust and gas, drifting through the galaxy for eons. Eventually, this cosmic dust gathered into the cloud that formed our solar system and Earth. The gold that humans mine from deep within the planet arrived here from those ancient stellar collisions. Every gold ring, every coin, every circuit board carries this history of cosmic violence transformed into beauty. Gold atoms are travelers from distant explosions, now resting quietly in the ground beneath our feet. Every carbon atom in your body was forged inside a dying star through a process called the triple alpha reaction. This happens when a star runs out of hydrogen fuel and begins to collapse under its own gravity. The core grows so hot that helium atoms can fuse together in groups of 3 to create carbon. This carbon then becomes the foundation for all organic chemistry and all known life. The carbon in your bones, your muscles, your brain, your DNA all came from stars that died before the sun was born. When those stars exhausted their fuel, they gently shed their outer layers into space, releasing carbon into the cosmic winds. This carbon drifted for millions of years until it gathered into new clouds that eventually formed our solar system. We are quite literally made of stardust, assembled from atoms that once burned at the hearts of ancient suns. Carbon connects every living thing on Earth to the stellar furnaces scattered across the universe. Technetium is the lightest element that has no stable isotopes and exists only artificially on Earth today. Every atom of technetium is radioactive and will eventually decay into other elements given enough time. Scientists first created this element in a laboratory in 1937 by bombarding other atoms with particles. Though technetium does not occur naturally on our planet, it is found in the spectra of certain dying stars. These stars produce technetium through nuclear reactions in their cores, but it decays before reaching Earth. The element has useful medical applications, particularly in diagnostic imaging, where its radioactivity helps doctors see inside the body. Technetium, is used in tens of millions of medical procedures every year around the world. Yet despite its usefulness, no sample of technetium will last forever, each atom slowly counting down to its transformation. This temporary element reminds us that not all matter is permanent, that even atoms have lifespans and endings. Iron is the last element a star can produce before it collapses catastrophically into a supernova explosion. Fusion reactions inside stars create heavier elements by combining lighter ones, but this process stops at iron. Creating elements heavier than iron requires more energy than the fusion reaction releases, so the process cannot sustain itself. When a massive star's core turns entirely to iron, fusion stops and the star loses the outward pressure that held it up against gravity. The core collapses in less than a second, falling inward at nearly a quarter the speed of light. This collapse triggers a rebound shock wave that tears the star apart in one of the most energetic events in the universe. The iron core that caused this catastrophe may be crushed into a neutron star or black hole. Iron, therefore, marks a cosmic boundary, the end point of stellar fusion, and the beginning of stellar death. Every iron atom on Earth came from such explosions, scattered across space, and eventually gathered here. Helium was discovered on the Sun before it was found on Earth by analyzing the spectrum of solar light. In 1868, astronomers noticed strange yellow lines in sunlight during a solar eclipse that did not match any known element. They realized this light came from an unknown substance and named it helium after Helios, the Greek word for sun. For nearly 30 years, helium existed only as a mysterious element visible in stellar spectra, but unknown on our planet. Finally, in 1895, scientists discovered helium trapped in uranium ore here on Earth. Helium forms underground when radioactive elements decay and release alpha particles, which are actually helium nuclei. The helium we use in balloons and scientific equipment comes from natural gas deposits where it is accumulated over millions of years. This light gas constantly escapes Earth's gravity and drifts away into space, never to return. Helium reminds us that Earth and Sun are made of the same materials, connected by chemistry across the vast distance. Oxygen is the third most abundant element in the entire universe, after hydrogen and helium. Stars create oxygen by fusing carbon atoms together in their cores when they grow old and massive enough. This oxygen then spreads through space when stars die, enriching the cosmic gas clouds that will form new generations of stars and planets. On Earth, oxygen makes up about half the mass of the rocks, water, and minerals that form the planet's crust. The oxygen we breathe comes from photosynthesis in plants and ocean algae that split water molecules and release oxygen gas. Every breath you take brings oxygen into your lungs where it binds to iron in your blood cells. That oxygen then travels through your body, providing energy to every cell through controlled combustion. Without oxygen, there would be no fire, no rust, no breath, no complex life as we know it. This element connects the air we breathe to the hearts of massive stars scattered across the galaxies. Francium is so rare that less than 30 grams exist naturally on Earth at any given moment in time. This element is intensely radioactive, with a half-life of just 22 minutes for its most stable isotope. Francium forms as a decay product of heavier radioactive elements like uranium and thorium buried deep in the Earth. Almost as soon as an atom of francium appears, it decays into other elements, making it nearly impossible to accumulate. Scientists have never been able to gather enough francium to see it with the naked eye or study its bulk properties. Everything known about francium comes from studying individual atoms or very small samples containing only a few thousand atoms. If you could somehow gather enough francium to see, it would likely vaporize immediately from the heat of its own radioactivity. This ghost element appears and vanishes continuously in the rocks beneath our feet, present but nearly impossible to grasp. Elements heavier than iron cannot be created by normal stellar fusion and require the extreme conditions of supernova explosions. When a massive star explodes, the shock wave creates temperatures and pressures far beyond anything possible in normal stellar cores. In these conditions, atomic nuclei are bombarded with so many neutrons that they rapidly gain mass and transform into heavier elements. This rapid neutron capture process happens in just a few seconds, but creates most of the heavy elements in the universe. Elements like gold, platinum, uranium, and lead all formed this way in the final explosive moments of dying stars. The debris from these explosions spreads through space, carrying heavy elements into new regions of the galaxy. Over billions of years, this enriched material gathers into new stars and planets, bringing heavy elements to places like Earth. Every heavy element on our planet is a remnant of ancient stellar explosions. The universe builds complexity through destruction, creating the heaviest atoms in moments of catastrophic violence. Phosphorus in your DNA was created in the final explosive moments of a massive star's death. This essential element forms during supernova nucleosynthesis when neutrons flood into atomic nuclei during the explosion. Phosphorus atoms then drift through space for millions or billions of years before gathering into new solar systems. On Earth, phosphorus became part of the chemistry that allows DNA to store genetic information in long, stable molecules. The backbone of every DNA strand is built from alternating phosphorus and sugar molecules that hold the genetic code. Without phosphorus, there would be no DNA, no RNA, no way for life to store and transmit information across generations. This element also stores and transfers energy in cells through molecules like ATP. Every thought you have, every movement you make depends on phosphorus released from an exploding star. We carry ancient stellar violence inside every cell, transformed into the quiet chemistry of life. The human body contains trace amounts of uranium and thorium from the formation of Earth billions of years ago. These radioactive elements were created in supernova explosions and neutron star collisions before our solar system existed. When Earth formed from the collapsing cloud of gas and dust, uranium and thorium were mixed into the rocks and soil. Over time, these elements entered the food chain through plants that absorb minerals from the ground. Animals eat the plants, and humans eat both plants and animals, bringing tiny amounts of radioactive elements into our bodies. The radiation from these trace amounts is incredibly small and poses no danger to human health. In fact, the potassium in your body is slightly more radioactive than the uranium. These ancient radioactive atoms are now part of your bones and tissues, linking you directly to the explosive deaths of stars. They remind us that even the most exotic elements eventually become woven into the fabric of ordinary life. Californium, E252, emits neutrons spontaneously without any external trigger and is worth approximately $27 million per gram. This incredibly rare synthetic element was first created in a laboratory in 1950 by bombarding curium with alpha particles. Only a few grams of californium are produced each year in specialized nuclear reactors around the world. The element's spontaneous neutron emission makes it valuable for starting up nuclear reactors and for detecting metals and moisture in materials. Californium is also used in cancer treatment, where its neutron radiation can destroy tumors that resist conventional radiation therapy. Despite its usefulness, the element is intensely radioactive with a half-life of about 2.5 years. A single microgram of californium-252 produces millions of neutrons every second, making it one of the most active neutron sources available. This element exists only because humans learned to recreate the nuclear processes that happen inside stars. Californium represents our ability to make matter that nature no longer produces on Earth. Bismuth was thought to be stable for centuries, but is actually radioactive, with a half-life longer than the age of the universe. For most of human history, bismuth seemed to be a permanent, non-radioactive metal like iron or copper. Scientists only discovered its radioactivity in 2003 using extremely sensitive instruments that could detect rare decay events. Bismuth-209 has a half-life of about 19 quintillion years, which means only a tiny fraction of bismuth atoms decay even over billions of years. This makes bismuth effectively stable for any practical purpose, yet it is technically radioactive and slowly transforming into other elements. The discovery changed our understanding of which elements are truly permanent and which are just very slow to change. Every bismuth atom will eventually decay, but the process takes so long that most will outlast the stars. This element sits on the boundary between stability and radioactivity, between the eternal and the temporary. It reminds us that even what seems permanent is slowly, imperceptibly changing. Silicon makes up nearly 28% of Earth's crust, but is vanishingly rare in the human body. This element forms the basis of most rocks, sand, and soil that cover the planet's surface. Silicon bonds readily with oxygen to create silicate minerals that give Earth its solid foundation. Yet despite being everywhere around us, silicon plays almost no role in human biology or the biology of most living things. Our bodies contain perhaps a few grams of silicon, mostly in connective tissues, compared to kilograms of carbon, hydrogen, and oxygen. Life on Earth chose carbon as its foundation element instead of silicon, even though silicon is far more abundant. Scientists sometimes wonder if life on other planets might be based on silicon rather than carbon chemistry. Silicon's abundance shows us that what is common is not always what is useful for life. The rocks beneath our feet and the life that walks upon them are built from entirely different elemental foundations. Gallium will melt in your hand at body temperature, but remains solid at room temperature. This silvery metal has a melting point of just 29.76 degrees Celsius, which is warmer than a cool room, but cooler than human skin. If you hold a piece of gallium in your palm, your body heat will slowly turn it from solid to liquid in a fascinating display. The metal pools in your hand like mercury, but is far less toxic and safer to handle. When the liquid gallium cools down again, it solidifies back into its metallic form without any change to its properties. Gallium is used in semiconductors, LEDs, and solar panels because of its electronic properties at various temperatures. The element also expands when it solidifies, which is unusual since most materials contract when they freeze. Gallium's low melting point makes it perfect for certain thermometers and heat transfer applications. This element blurs the line between solid and liquid in our everyday temperature range. Astatine is the rarest naturally occurring element with less than 1 ounce existing on Earth at any given moment. This element is so rare because it is intensely radioactive, with a half-life of only 8.1 hours for its longest-lived isotope. Astatine forms as a decay product of uranium and thorium, but it decays away almost as quickly as it appears. Scientists estimate that the entire Earth's crust contains less than 30 grams of astatine at any time. The element was first synthesized in a laboratory in 1940 before it was confirmed to exist in nature. Because astatine decays so quickly, it has never been accumulated in visible quantities, and all its properties must be inferred from tiny samples. If you could somehow gather enough astatine to see, it would likely vaporize from its own radioactive heat within seconds. This ghost element reminds us that the periodic table contains entries that barely exist in our world. Some elements are more like fleeting ideas than solid matter. Aluminum was once more valuable than gold because it was extraordinarily difficult to extract from its ore. In the mid-1800s, aluminum was considered a precious metal, despite being one of the most abundant elements in Earth's crust. The metal binds so tightly to oxygen in its ores that separating them required enormous amounts of energy and effort. Napoleon III reportedly displayed his finest aluminum tableware at state dinners while guests used gold utensils. The Washington Monument was capped with aluminum in 1884, when the metal was still rare and expensive. Everything changed in 1886, when scientists discovered an efficient electrical process for extracting aluminum from ore. Within decades, aluminum went from precious metal to everyday material used in foil, cans, and construction. The price dropped by over 99% as production methods improved. This transformation shows how technology can turn scarcity into abundance almost overnight. Cobalt gives blue glass its distinctive color and is essential for vitamin B12 in all animals. This metal has been used for thousands of years to create brilliant blue pigments in pottery, glass, and paint. Ancient civilizations valued cobalt blue even though they did not understand what element created the color. The blue comes from the way cobalt atoms absorb and reflect light when mixed into glass or ceramic materials. In biology, cobalt sits at the center of the vitamin B12 molecule, which is essential for making red blood cells and maintaining nerve function. Without cobalt, animals cannot produce healthy blood or maintain their nervous systems properly. Humans need only trace amounts of cobalt, all of it arriving through vitamin B12 in food from animal sources. The same element that colors ancient glass also enables fundamental life processes in every animal on Earth. Cobalt connects human artistry with the basic chemistry of life. The Big Bang created only hydrogen, helium, and trace amounts of lithium in the first 3 minutes after the universe began. These three lightest elements formed when the universe was still unimaginably hot and dense, filled with a soup of particles and energy. As space expanded and cooled, protons and neutrons began to stick together, forming the first atomic nuclei. Hydrogen formed first with just one proton, then helium with 2 protons and 2 neutrons, and finally, tiny amounts of lithium with 3 protons. The universe cooled too quickly for heavier elements to form, so these 3 were all that existed for hundreds of millions of years. every other element on the periodic table had to wait for the first stars to form and begin their nuclear fusion. The early universe was a simple place with only these three elements and the light they created. All the complexity and diversity of matter we see today came later, built slowly over billions of years. Those first three elements still make up over 99% of all normal matter in the universe. Copper is one of the few metals that is naturally antibacterial and kills bacteria on contact. When bacteria land on a copper surface, copper ions disrupt their cell membranes and damage their DNA, leading to death within hours. This property made copper valuable for water pipes and door handles long before people understood why it prevented disease. Ancient civilizations noticed that water stored in copper vessels stayed fresh longer than water in other containers. Modern hospitals are rediscovering copper's antibacterial properties by installing copper surfaces in high-touch areas. Studies show that copper surfaces reduce bacterial contamination by over 99% compared to stainless steel. The metal's antimicrobial effect works continuously without any power source or maintenance required. Copper also conducts electricity exceptionally well, making it essential for wiring in nearly every electronic device. This element protects us from infection while powering the modern world. Nitrogen makes up 78% of Earth's atmosphere, but was forged in massive stars over billions of years through nuclear fusion. This element forms when carbon atoms in a star's core capture additional protons during the carbon-nitrogen-oxygen cycle. Stars continuously create nitrogen through this process, which also produces the energy that makes them shine. When these stars die, they release nitrogen into space where it drifts for eons before gathering into new planetary systems. On Earth, nitrogen became the dominant atmospheric gas, partly because it is chemically unreactive and doesn't easily combine with rocks or water. Living things need nitrogen to build proteins and DNA, but most cannot use the nitrogen gas floating in the air. Special bacteria in soil and plant roots convert atmospheric nitrogen into forms that plants can absorb and use. Without these bacteria, life would struggle to access one of its most essential building blocks. The nitrogen you breathe was created in ancient stars and transformed by microbes into the chemistry of life. Xenon has been used as an anesthetic in surgery and is currently used in ion propulsion systems for spacecraft. This heavy, noble gas is chemically unreactive under normal conditions, which makes it safe for medical use. When patients breathe xenon mixed with oxygen, it produces unconsciousness without the side effects of many traditional anesthetics. The gas works by affecting nerve signal transmission in the brain, though the exact mechanism is still being studied. In space, xenon is ionized and accelerated to high speeds to provide gentle but continuous thrust for satellites and deep space probes. Ion engines using xenon can operate for years, slowly building up enough speed to reach distant destinations. The Dawn spacecraft used xenon propulsion to visit the asteroid belt and study two different dwarf planets. This element bridges medicine and space exploration, carrying humans into unconsciousness and machines into the cosmos. Xenon reminds us that even unreactive elements can be harnessed for remarkable purposes. Mercury is the only metal that remains liquid at room temperature except for gallium, which melts near body heat. This silvery liquid metal has fascinated humans for thousands of years with its strange properties and behavior. Mercury atoms bond weakly to each other, which keeps them flowing freely at temperatures where most metals are solid. The element conducts electricity, reflects light like a mirror, and forms perfect spheres when placed on flat surfaces. Ancient civilizations used mercury in medicine and alchemy, not understanding its toxicity to the human nervous system. Mercury vapor and mercury compounds can cause serious damage to the brain and kidneys with prolonged exposure. Today, mercury is used in some scientific instruments, fluorescent lights, and dental amalgams, though safer alternatives are gradually replacing it. The element accumulates in fish that humans eat, making mercury pollution a continuing environmental concern. This beautiful liquid metal demonstrates that what appears magical can also be dangerous. Sulfur exists in amino acids that fold proteins into their functional three-dimensional shapes throughout all living things. Two amino acids, cysteine and methionine, contain sulfur atoms that create special bonds helping proteins maintain their structure. These sulfur-sulfur bridges act like molecular staples, holding protein chains in the precise shapes needed for life. Without sulfur bonds, proteins would unfold and lose their ability to function as enzymes, structural components, and chemical messengers. Sulfur also plays roles in energy production within cells and in various metabolic processes. The element is abundant on Earth, forming distinctive yellow crystals near volcanic vents and hot springs. Ancient civilizations knew sulfur as brimstone and associated it with fire and transformation. Burning sulfur creates sulfur dioxide, which has a sharp, choking smell that makes volcanic regions distinctive. This element connects the heat of volcanic Earth to the folded complexity of every protein in your body. Plutonium does not occur naturally on Earth anymore, but was present in trace amounts when the planet first formed 4.5 billion years ago. This element is created in supernova explosions and during certain nuclear reactions, but it decays relatively quickly on geological timescales. Any plutonium that was present when Earth formed has long since decayed into other elements. Today, all plutonium on Earth is created artificially in nuclear reactors when uranium atoms absorb neutrons. Plutonium-239 is fissile, meaning it can sustain a nuclear chain reaction, making it useful for nuclear power and weapons. The element is intensely radioactive and highly toxic if ingested or inhaled, requiring careful handling and containment. Some plutonium-238 is used to power deep space probes like Voyager and New Horizons through radioactive decay heat. These spacecraft carry pieces of Earth-made plutonium to the edge of the solar system and beyond. Plutonium represents human ability to recreate elements that no longer exist naturally on our planet. Sodium reacts explosively with water because it desperately releases its single outer electron to achieve a stable configuration. This soft silvery metal has one electron in its outermost shell, which it wants to give away to become more stable. When sodium touches water, it rapidly donates that electron, creating sodium ions and releasing hydrogen gas. The reaction generates so much heat that the hydrogen gas often ignites, creating a flame that dances across the water surface. Pure sodium is so reactive that it must be stored in oil to prevent it from reacting with moisture in the air. Yet when sodium combines with chlorine, another dangerous element, they form ordinary table salt that is essential for life. Sodium ions help control fluid balance in cells and are crucial for transmitting nerve signals throughout your body. Every thought and muscle movement depends on sodium ions flowing across cell membranes. This element demonstrates how reactive and dangerous substances can become safe and essential through chemistry. Cadmium absorbs neutrons efficiently and is used in nuclear reactor control rods to regulate the speed of nuclear reactions. When cadmium is inserted into a reactor core, it captures neutrons that would otherwise split uranium atoms and continue the chain reaction. By adjusting how far the cadmium rods are inserted, operators can control how much power the reactor produces. The element is soft, silvery blue, and was discovered in 1817 as an impurity in zinc ore. Cadmium was once widely used in rechargeable batteries, pigments, and coatings, but its toxicity has led to restrictions on many uses. The element accumulates in kidneys and can cause bone and organ damage with chronic exposure. Smoking tobacco is a major source of cadmium exposure, since tobacco plants absorb it from soil. Despite its dangers, cadmium remains valuable for controlling nuclear reactions and in specialized industrial applications. This element sits at the intersection of nuclear physics and human health concerns. Carbon can bond with itself in endless ways, creating millions of known organic compounds and countless more yet to be discovered. This versatility comes from carbon's ability to form 4 strong bonds arranged in different geometric patterns. Carbon atoms link together in chains, rings, sheets, and 3-dimensional frameworks, each structure creating different properties. Diamond and graphite are both pure carbon, but have completely different characteristics because their atoms are arranged differently. Diamond is the hardest natural material, while graphite is soft enough to write with as pencil lead. More recently discovered carbon forms include fullerenes, which are hollow spheres of carbon atoms, and graphene, which is a single layer of carbon atoms arranged in a honeycomb pattern. Living things exploit carbon's versatility to build DNA, proteins, fats, sugars, and all the other molecules that make life possible. The carbon in your body has been recycled through countless living things over billions of years. This element is the foundation of organic chemistry and the scaffold upon which life is built. Titanium is as strong as steel, but 45% lighter and highly resistant to corrosion in harsh environments. This metal was discovered in 1791, but was difficult to extract in pure form until the 20th century. Titanium's strength-to-weight ratio makes it ideal for aircraft, spacecraft, and high-performance sporting equipment. The metal is also biocompatible, meaning the human body does not reject it, making it perfect for medical implants and artificial joints. Titanium dioxide is a bright white pigment used in paints, sunscreens, and food coloring. The element is relatively abundant in Earth's crust, but is energy intensive to refine from its ore. When titanium burns, it reacts with nitrogen in the air to form a golden-colored nitride coating. This coating is extremely hard and is used to protect cutting tools and create decorative finishes. Titanium bridges the worlds of aerospace engineering, medicine, and everyday consumer products. Radium glows in the dark with a faint blue light because of its intense radioactivity exciting the surrounding air. This element was discovered by Marie and Pierre Curie in 1898 after years of processing tons of uranium ore. Radium is millions of times more radioactive than uranium and was initially celebrated as a miracle substance. In the early 20th century, radium was added to paint for watch dials, mixed into health tonics, and used in various consumer products. Workers who painted radium on watch dials suffered terrible injuries and deaths from radiation exposure, leading to some of the first occupational safety laws. Today we understand that radium is extremely dangerous, replacing calcium in bones and causing cancer. The element is still used in some medical treatments for cancer, where its radiation can destroy tumors. Radium's story shows how scientific discoveries can be both celebrated and feared, and how understanding grows through tragedy. This glowing element taught humanity to respect the power hidden within atoms. Potassium in bananas is very slightly radioactive because of the isotope potassium-40 that exists naturally in all potassium sources. About 1 in every 10,000 potassium atoms is the radioactive potassium-40 isotope, which has a half-life of over 1 billion years. This isotope decays slowly by releasing beta particles, creating trace amounts of radiation in potassium-containing foods. The human body contains about 140 grams of potassium, making your body naturally radioactive with thousands of potassium-40 atoms decaying every second. This internal radiation is completely harmless because the amount is tiny and your body has evolved to handle it. Potassium is essential for nerve function, muscle contraction, and maintaining proper heart rhythm. The element exists in all cells, where it balances sodium and helps control water movement across membranes. Eating a banana exposes you to slightly less radiation than you receive from cosmic rays in a few minutes. This radioactive element quietly ticks away inside you, powering your nervous system while slowly transforming into other atoms. Neon lights actually contain various gases that glow different colors when electricity passes through them. Pure neon gas glows orange-red when electrified, which is why classic neon signs have that warm, reddish color. To create other colors, manufacturers use different noble gases or mix in other substances with neon. Argon produces a pale blue light. Helium creates yellow or pink, and mercury vapor makes blue or white. The glass tubes can also be coated with phosphors that change the color of the light they produce. Neon is the 5th most abundant element in the universe, but makes up only a tiny fraction of Earth's atmosphere. The element is extracted from air by cooling it until it liquefies, then separating the different gases by their boiling points. Neon was discovered in 1898 and was considered rare and precious for decades. These glowing tubes transformed city nightscapes and became symbols of modernity and commercial culture. Lead is so dense that it effectively blocks X-rays and gamma rays, making it essential for medical and nuclear shielding. The element contains 82 protons in its nucleus, making each atom heavy, enough to stop high-energy radiation. Lead sheets and aprons protect patients and medical workers from scattered radiation during X-ray procedures. Nuclear power plants use lead in radiation shields around reactor cores and radioactive materials. The metal is soft, malleable, and has a low melting point, which made it useful for pipes and roofing for thousands of years. Ancient Romans used lead extensively in plumbing, which may have contributed to health problems in their civilization. We now know that lead is toxic to the nervous system, especially in developing children, causing learning difficulties and behavioral problems. Modern regulations have removed lead from gasoline, paint, and most consumer products. This heavy metal protects us from radiation while also reminding us that useful materials can have hidden dangers. Chlorine is a poisonous yellow-green gas when pure, but becomes essential table salt when chemically bonded to sodium. Pure chlorine gas burns the lungs and eyes and was used as a chemical weapon in World War I. The element is so reactive that it never exists freely in nature and is always found combined with other elements. Chlorine bonds with sodium to form sodium chloride, common table salt which is necessary for life. This transformation shows how chemistry can completely change an element's properties through bonding. Chlorine is used to disinfect drinking water and swimming pools because it kills bacteria and other harmful microorganisms. The chlorine in pools creates that distinctive smell, especially when it reacts with organic compounds from swimmers. Your stomach produces hydrochloric acid for digestion using chlorine atoms bonded to hydrogen. This dangerous gas has become domesticated through chemistry into substances that protect and sustain human life. Magnesium burns with an intensely bright white light and was used in early photography flashes to illuminate subjects. When magnesium metal ignites, it reacts vigorously with oxygen in the air, releasing tremendous amounts of light and heat. The reaction is so bright that it can damage eyes if viewed directly without protection. Photographers in the late 1800s and early 1900s used magnesium powder as flash powder for indoor and nighttime photography. Today, magnesium is still used in fireworks, flares, and incendiary devices for its brilliant white light. The element is essential for life, sitting at the center of every chlorophyll molecule that makes plants green. Magnesium ions activate hundreds of enzymes in the human body and are crucial for bone formation and muscle function. Despite being one of the most abundant elements in Earth's crust, magnesium deficiency is common in modern diets. This element literally makes the world green and bright while quietly enabling countless biological processes. Arsenic is a poisonous metalloid, but is also used in trace amounts in some semiconductors and specialized applications. This element has been infamous throughout history as a poison because it is tasteless, odorless, and was difficult to detect. Arsenic disrupts cellular energy production, causing organ failure and death at sufficient doses. Despite its toxicity, arsenic compounds were once used in medicines and are still used in some cancer treatments at carefully controlled doses. The element is a metalloid, meaning it has properties between metals and nonmetals, making it useful in electronic materials. Arsenic is added to certain semiconductor alloys to modify their electrical properties for specialized applications. The element occurs naturally in some groundwater, particularly in regions where rock formations contain arsenic minerals. Long-term exposure to arsenic-contaminated water causes skin lesions, cancer, and cardiovascular problems. This element demonstrates the fine line between poison and medicine, between danger and utility. Bromine is one of only two elements that are liquid at room temperature, along with mercury. This dark, reddish-brown liquid evaporates easily, producing toxic vapors that irritate eyes and lungs. The name bromine comes from the Greek word bromos, meaning stench, referring to its strong, unpleasant smell. Bromine is found dissolved in seawater and in underground brine deposits. Never occurring free in nature, the element is extracted from seawater by chemical processes that concentrate and isolate it from salt water. Bromine compounds were once used extensively in flame retardants added to furniture, electronics, and textiles. The element has also been used in photography, water purification, and the production of certain pharmaceuticals. Some brominated compounds are now being phased out because of environmental and health concerns. This liquid element connects the chemistry of the sea to human technology and safety applications. Calcium phosphate gives bones their hardness and strength throughout the skeletal structure of all vertebrate animals. This mineral compound forms the solid framework that bones are built upon, providing structural support for bodies. Calcium and phosphorus combine in a specific crystal structure called hydroxyapatite that makes bones rigid yet slightly flexible. Without calcium phosphate, bones would be soft, and unable to support weight or protect internal organs. The human body contains about 1 kilogram of calcium, with 99% of it stored in bones and teeth. Bones are not static structures, but are constantly being broken down and rebuilt throughout life. Calcium also plays crucial roles in muscle contraction, nerve signaling, and blood clotting beyond its structural function. Phosphorus is equally important, forming the backbone of DNA and the energy currency molecule ATP. These two elements work together to create the framework that holds vertebrate bodies upright. Lithium is the lightest of all metals and floats easily on water despite being a solid metal. This soft silvery metal has only 3 protons in its nucleus, making it less dense than water. Lithium reacts with water, though less violently than sodium or potassium, releasing hydrogen gas as it forms lithium hydroxide. The element is essential for rechargeable lithium-ion batteries that power smartphones, laptops, and electric vehicles. These batteries can store large amounts of energy in a lightweight package, enabling portable electronics and electric transportation. Lithium is also used in medicine to treat bipolar disorder, though scientists still do not fully understand how it stabilizes mood. The element is relatively rare on Earth because light elements like lithium are not efficiently produced in stars. Most lithium was created in the Big Bang, making it one of the oldest elements in existence. This light metal powers modern technology while also affecting human brain chemistry in ways we are still discovering. Zinc is required for over 300 enzymes in the human body to function properly. These enzymes are proteins that speed up chemical reactions necessary for life, and many need zinc atoms to work. Zinc plays roles in immune function, wound healing, protein synthesis, and DNA production throughout the body. The element is essential for proper taste and smell, and deficiency can cause loss of these senses. Zinc is found throughout Earth's crust, usually combined with sulfur in the mineral sphalerite. The metal has been used for thousands of years, particularly in brass, which is an alloy of copper and zinc. Galvanized steel is coated with zinc to protect it from rust and corrosion in harsh environments. Zinc oxide is used in sunscreens and diaper creams because of its gentle protective properties. This essential element works invisibly in cells while also protecting structures and skin from damage. Nickel is magnetic at room temperature and makes up about 10% of the Earth's core, along with iron. This metal is one of only 4 elements that are naturally magnetic at room temperature, the others being iron, cobalt, and gadolinium. Scientists believe Earth's core is a mixture of molten iron and nickel that generates the planet's magnetic field through convection currents. This magnetic field protects Earth from harmful solar radiation and cosmic particles that would otherwise strip away the atmosphere. Nickel is used extensively in alloys to make stainless steel more resistant to corrosion and heat. The metal is also used in rechargeable batteries, coins, and electroplating to protect other metals from corrosion. Some people develop allergic reactions to nickel in jewelry, causing skin irritation and rashes. Nickel's name comes from the German word Kupfernickel, which miners used for ore that looked like copper but yielded this different metal. This element connects the protection offered by Earth's magnetic shield to everyday objects in our pockets and homes. Beryllium is toxic and carcinogenic, but is also used in aerospace alloys because of its exceptional lightweight and strength. This metal is less dense than aluminum, but stiffer than steel when comparing equal weights. Beryllium's combination of properties makes it valuable for aircraft components, satellites, and spacecraft, where every gram matters. The metal is transparent to X-rays, making it useful for the windows of X-ray tubes used in medical imaging. Despite its usefulness, inhaling beryllium dust or fumes can cause a serious lung disease called chronic beryllium disease. This condition causes inflammation and scarring in the lungs that can progress even after exposure ends. Workers who handle beryllium must use strict safety procedures to avoid breathing the dust or allowing it to contact skin. Beryllium also plays a role in nuclear weapons, where it is used as a neutron reflector and initiator. This lightweight element demonstrates how the same properties that make materials valuable can also make them dangerous. Chromium gives rubies their red color and emeralds their green color, depending on the crystal structure surrounding the chromium atoms. When chromium atoms replace some aluminum atoms in corundum, the resulting crystal is red ruby, one of the most valued gemstones. When chromium atoms are present in beryl crystals, they create the green color of emeralds. The same element produces different colors because the surrounding crystal structure affects how chromium absorbs and reflects light. Chromium metal itself is silvery and is used to create shiny, protective coatings on other metals. Chrome plating makes surfaces resistant to corrosion while giving them a mirror-like finish. Stainless steel contains chromium, which forms an invisible protective layer that prevents rust and corrosion. The element's name comes from the Greek word chroma, meaning color, because chromium compounds come in many vivid colors. This element transforms ordinary rocks into precious gems and protects everyday objects from decay. Selenium is essential for thyroid hormone metabolism, despite being toxic in larger amounts than the body needs. This element is required for enzymes called selenoproteins that protect cells from oxidative damage and help regulate thyroid function. The human body needs only trace amounts of selenium, with too little causing health problems and too much causing toxicity. Brazil nuts are exceptionally high in selenium, with just a few nuts providing more than the daily requirement. Selenium was discovered in 1817 and was named after Selene, the Greek goddess of the moon. The element is used in photocells because its electrical conductivity increases when exposed to light. Selenium is also used in glass manufacturing to remove color or to create ruby red glass. In photocopiers and laser printers, selenium-coated drums transfer images through light-controlled electrical charge. This element occupies the narrow range between essential nutrient and poison, between benefit and harm. Iodine is necessary for thyroid function, and its deficiency causes goiter, an enlargement of the thyroid gland affecting millions worldwide. The thyroid gland uses iodine to produce hormones that regulate metabolism, growth, and development throughout the body. Without enough iodine, the thyroid cannot make sufficient hormones and enlarges in an attempt to capture more iodine from the blood. Iodine deficiency is especially harmful during pregnancy and early childhood, causing developmental delays and intellectual disabilities. Most table salt is now fortified with iodine to prevent deficiency diseases in populations far from the sea. Iodine is found naturally in seawater and is concentrated by seaweed and seafood, making coastal populations less likely to be deficient. The element forms dark purple crystals that sublime directly from solid to purple vapor when heated. Tincture of iodine was once commonly used as an antiseptic though it has been largely replaced by less irritating alternatives. This element connects ocean chemistry to human brain development and the prevention of ancient diseases. Boron is essential for plant cell walls, but its exact role in animals is still being studied by scientists. Plants need boron to form and maintain cell walls, transport sugars, and reproduce successfully. Without adequate boron, plants develop hollow stems, brittle leaves, and fail to produce seeds or fruits. The element is found in soil, but some agricultural areas have naturally low boron levels requiring fertilizer supplements. In animals and humans, boron appears to play roles in bone health, hormone regulation, and brain function, though the mechanisms are not fully understood. Boron compounds have been used in everything from detergents to fiberglass to rocket propulsion fuels. The element forms unusual chemical bonds that allow it to create a wide variety of compounds with different properties. Borosilicate glass, which contains boron, resists thermal shock and is used in cookware and laboratory equipment. This element remains somewhat mysterious despite being essential for life and widely used in technology. Fluorine is the most reactive element and attacks almost every other substance it contacts with explosive violence. This pale yellow gas will react with nearly every element except a few noble gases like helium and neon. Fluorine is so reactive that it can make asbestos and water burst into flames on contact. Scientists struggled for decades to isolate pure fluorine because it would immediately attack any container or equipment. When fluorine reacts with metals, it often forms extremely stable compounds that are nearly indestructible. Teflon, the non-stick coating on cookware, is a polymer of carbon and fluorine that is remarkably resistant to heat and chemicals. Fluoride compounds are added to water and toothpaste because they strengthen tooth enamel and prevent cavities. The element is also used to enrich uranium for nuclear reactors and weapons by forming uranium hexafluoride gas. This most reactive element has been tamed into substances that protect teeth and prevent food from sticking to pans. Argon makes up nearly 1% of Earth's atmosphere, but is completely inert and non-reactive under normal conditions. This noble gas does not form chemical compounds with other elements under ordinary circumstances. Argon exists as single atoms that drift through the air without bonding to anything around them. The gas is used to fill incandescent light bulbs to prevent the hot filament from reacting with oxygen and burning out. Welders use airgun as a shielding gas to protect hot metal from reacting with oxygen and nitrogen in the air. Airgun is also used to preserve old documents and artifacts by displacing reactive oxygen that would cause decay. The element's name comes from the Greek word argos, meaning lazy or inactive, because of its chemical inertness. Argon is produced industrially by separating it from air through cooling and fractional distillation. This lazy element surrounds us constantly, yet participates in nothing, drifting through air as a perpetual observer. Manganese is essential for photosynthesis in plants and bone formation, in animals throughout the living world. In plant chloroplasts, manganese atoms help split water molecules to release oxygen during photosynthesis. This process provides the oxygen that all animals breathe and is fundamental to life on Earth. In animals, manganese activates enzymes involved in building bones, metabolizing amino acids, and processing cholesterol. The human body contains only about 12 milligrams of manganese, but this small amount is essential for health. Manganese deficiency is rare, but can cause bone problems, skin rashes, and changes in hair color. The element is used in steel making to remove oxygen and sulfur impurities and to make alloys harder and more resistant to wear. Manganese dioxide is used in dry cell batteries and as a catalyst in various chemical reactions. This element connects the green of photosynthesis to the strength of bones and steel. Tellurium makes your breath smell like garlic if you ingest even tiny amounts of this element. The body converts tellurium into dimethyl telluride, a volatile compound that is exhaled through the lungs, creating a distinctive odor. This garlicky smell can persist for weeks after exposure, making tellurium one of the most easily detectable elements through smell. Tellurium is relatively rare on Earth, but is more common in the universe than on our planet. The element is used in alloys to improve machinability and in thermoelectric devices that convert heat directly to electricity. Cadmium telluride is used in some solar panels because of its excellent light-absorbing properties. Tellurium was discovered in 1782 in gold ore from Transylvania, though it was initially mistaken for antimony. The element sits just below selenium on the periodic table and has similar but less important biological roles. This rare element leaves its mark through smell, creating a signature that lingers long after the exposure ends. Cerium is the most abundant rare earth element despite its classification as rare, making up more of Earth's crust than copper or lead. The term rare earth elements is somewhat misleading because many of them are not particularly rare in absolute terms. Cerium is found in various minerals and is more common than many familiar metals people encounter daily. The element was discovered in 1803 and named after the asteroid Ceres, which itself was discovered just 2 years earlier. Cerium oxide is used as a polishing powder for glass and mirrors because of its hardness and ability to remove material smoothly. The element is also used in catalytic converters for vehicles, helping to reduce harmful emissions from exhaust gases. Self-cleaning ovens use cerium oxide in coatings that help break down food residue at high temperatures. Some cerium compounds glow when exposed to ultraviolet light, making them useful in various detection and lighting applications. This supposedly rare element is actually all around us, hidden in everyday technologies and industrial processes. Vanadium strengthens steel alloys and may play a role in some biological enzyme systems, though its function is not fully understood. When added to steel in small amounts, vanadium creates extremely strong and tough alloys, resistant to wear and shock. Vanadium steel is used in tools, springs, and high-speed machinery that must withstand extreme stresses. The element was discovered and named twice because early samples were impure and scientists did not realize they were studying the same substance. Vanadium compounds display beautiful colors ranging from yellow to blue to green, depending on their oxidation state. Some marine organisms, like certain sea squirts, concentrate vanadium in their blood, though scientists still debate why. In mammals, trace amounts of vanadium appear to affect insulin sensitivity and glucose metabolism. The element sits at the boundary between confirmed essential nutrient and possible biological role. This strong metal may be quietly participating in life processes we have yet to fully understand. Molybdenum is essential for nitrogen fixation in soil bacteria that feed plants and ultimately all animal life. Special bacteria convert atmospheric nitrogen gas into ammonia that plants can absorb and use to build proteins. These bacteria require the enzyme nitrogenase, which contains molybdenum at its active center where the chemistry happens. Without molybdenum, nitrogen fixation would be impossible and plants would struggle to obtain this essential nutrient. The element is also necessary for human enzymes that break down certain amino acids and other compounds. Molybdenum is used in steel alloys to increase strength, hardness, and resistance to corrosion at high temperatures. The element has one of the highest melting points of any pure element at 2,623 degrees Celsius. Molybdenum disulfide is an excellent lubricant that works even in extreme heat, vacuum, and radiation conditions. This element connects soil bacteria to steel manufacturing, linking the chemistry of life to the demands of industry. Tungsten has the highest melting point of all metals at 3,422 degrees Celsius. This extreme temperature resistance makes tungsten ideal for light bulb filaments that must glow white hot without melting. The element is also incredibly dense, nearly the same density as gold, making it useful for counterweights and military applications. Tungsten carbide is one of the hardest substances known and is used in cutting tools, mining equipment, and armor-piercing ammunition. The element's name comes from the Swedish words tungsten, meaning heavy stone, reflecting its exceptional density. Tungsten is used in rocket nozzles and furnace heating elements that must withstand temperatures that would melt most other materials. The element also has the lowest vapor pressure of all metals, meaning it does not easily evaporate even at extreme temperatures. Scientists are studying tungsten as a potential material for fusion reactor walls that must handle the intense heat of controlled fusion reactions. This metal defines the upper limits of temperature resistance, pushing the boundaries of what materials can endure. Strontium-90 is a dangerous radioactive fallout product from nuclear weapons and accidents that mimics calcium in bones and accumulates there. When nuclear weapons detonate or reactors fail, they release various radioactive isotopes, including strontium-90. The human body cannot distinguish between calcium and strontium because they are chemically similar elements in the same column of the periodic table. If strontium-90 enters the body through food or water, it deposits in bones and teeth where it emits radiation for years. This internal radiation can damage bone marrow and cause leukemia and bone cancer. Strontium-90 has a half-life of about 29 years, meaning it remains hazardous for centuries after release. The element was a major health concern from atmospheric nuclear weapons testing in the 1950s and 60s. After the Chernobyl disaster, strontium-90 contaminated large areas, requiring evacuations and restrictions on agriculture. This radioactive element serves as a reminder that chemistry can be twisted into weapons and that accidents carry consequences lasting generations. Rubidium ignites spontaneously when exposed to air and reacts even more violently than sodium when placed in water. This soft, silvery metal must be stored under oil or in sealed containers to prevent contact with oxygen and moisture. When rubidium touches water, it reacts explosively, producing hydrogen gas and rubidium hydroxide while releasing tremendous heat. The reaction is violent enough to ignite the hydrogen gas, creating flames and potentially shattering containers. Rubidium was discovered through spectroscopy in 1861, identified by the deep red lines it produces in flame tests. The element's name comes from the Latin rubidus, meaning deepest red, referring to these spectral lines. Rubidium is used in atomic clocks that are so precise they would lose less than 1 second in hundreds of millions of years. Some specialized vacuum tubes and photocells use rubidium because of its electronic properties. This explosive element has been tamed into some of the most precise timekeeping devices humanity has ever created. Cesium is so soft you can cut it with a butter knife and melts at just 28.5 degrees Celsius. This is the softest metal that is not liquid at room temperature, easily deforming under slight pressure. Cesium reacts even more violently with water than rubidium, producing explosions that can shatter glass containers. The element was discovered in 1860 through spectroscopy, identified by blue lines in its spectrum. Its name comes from the Latin cesius, meaning sky blue, referring to these spectral lines. Cesium is used in atomic clocks that define the second based on the vibration frequency of cesium atoms. These clocks are so accurate that they form the basis for international timekeeping and GPS satellite systems. Cesium is also used in drilling fluids for oil and gas wells because of its high density. This soft, reactive metal helps humanity measure time with extraordinary precision while also enabling energy exploration. Barium compounds glow green in fireworks and are used in medical imaging to make the digestive tract visible on X-rays. When barium salts are heated in fireworks, they produce a brilliant green color that is distinct and easily recognized. In medicine, patients drink barium sulfate before X-ray examinations of the stomach and intestines. Barium is opaque to X-rays, so it coats the digestive tract and makes it visible on the imaging, revealing ulcers, tumors, and other abnormalities. Pure barium metal is soft and silvery, but reacts readily with air and moisture, so it is never found free in nature. The element was discovered in 1808 and named after the Greek word baris, meaning heavy. Barium compounds are used in making glass, ceramics, and various industrial materials. Despite its usefulness, barium is toxic if consumed in forms other than the insoluble barium sulfate used in medical imaging. This element illuminates both fireworks displays and internal organs, serving celebration and diagnosis. Antimony has been used in cosmetics for thousands of years and in modern flame retardants to prevent fires. Ancient Egyptians used antimony compounds as black eyeliner, continuing a tradition that spread across many cultures. The element itself is a brittle, silvery metalloid that has properties between metals and nonmetals. Antimony is used in alloys with lead to make it harder and more resistant to corrosion in batteries. The element and its compounds are used extensively in flame retardants for textiles, plastics, and building materials. These compounds work by releasing gases that starve flames of oxygen when materials begin to burn. Antimony trioxide is also used in some plastics to increase their clarity and in making glass for television screens and optical applications. The element can be toxic in large doses, and some antimony compounds have been used as medicines for parasitic diseases. This ancient cosmetic ingredient now protects homes and possessions from the danger of fire. Indium is soft enough to leave a mark like pencil lead when rubbed on paper, making it one of the softest metals. This silvery white metal is extremely malleable and ductile, bending easily without breaking. Indium was discovered in 1863 through spectroscopy, identified by a bright indigo line in its spectrum. The element's name comes from indigo, the color that revealed its existence. Indium is used in touchscreens and flat panel displays as indium tin oxide, a transparent conductor of electricity. This allows screens to detect finger touches while remaining see-through for the display underneath. Indium is also used in some solders, especially for low-temperature applications where traditional solders might not work. The element seals well to glass and remains pliable even at very cold temperatures. This soft metal enables the touch-sensitive screens that have become ubiquitous in modern life, connecting fingers to digital worlds. thorium could potentially fuel nuclear reactors more safely than uranium because it produces less long-lived radioactive waste. This element is more abundant than uranium and is found in various minerals throughout Earth's crust. Thorium itself is not fissile, meaning it cannot sustain a nuclear chain reaction on its own. However, when thorium absorbs a neutron, it transforms into uranium-233, which is fissile and can fuel nuclear reactions. Thorium reactors would be more difficult to use for making nuclear weapons because they do not produce plutonium as a byproduct. The technology for thorium reactors exists, but has not been widely developed because uranium reactors were chosen early in nuclear history. Some countries are now researching thorium as a potentially cleaner and more abundant nuclear fuel for the future. Thorium is also radioactive and was once used in gas lantern mantles before the health risks were understood. This element represents a path not taken in nuclear energy, waiting to see if humanity will reconsider its potential. Praseodymium creates the yellow tint in welders' goggles by filtering out intense light wavelengths that could damage eyes. This rare earth element absorbs specific wavelengths of light while allowing others to pass through. When added to glass, praseodymium filters out the bright yellow sodium light that welding arcs produce. The tinted lenses protect welders' eyes from both visible light and ultraviolet radiation. Praseodymium is also used in creating powerful permanent magnets when combined with other rare earth elements. The element gives certain glasses a subtle green tint and is used in some specialized optical applications. Praseodymium was discovered in 1885 when scientists separated it from another rare earth element mixture. The name comes from the Greek words praseos didymos, meaning green twin, because of its green salts. This element protects human eyes from dangerous light while helping create the magnets that power modern technology. Neodymium makes the strongest permanent magnets when alloyed with iron and boron in a specific combination. These neodymium magnets are so powerful they can lift objects thousands of times their own weight. The magnets are found in computer hard drives, headphones, electric motors, and countless other devices. Neodymium iron boron magnets revolutionize technology by allowing smaller, more efficient motors and generators. The element is also used in lasers for various industrial, medical, and scientific applications. Neodymium gives glass a purple or violet color and is used in specialty optical filters. The element was discovered in 1885 by the same scientist who discovered praseodymium. Neodymium's name comes from the Greek neos didymos, meaning new twin, as it was separated from praseodymium. These powerful magnets have become essential to modern life, hidden in devices people use every day without knowing. Scandium is used in aluminum alloys to add strength for aerospace applications and sporting goods like baseball bats. Adding small amounts of scandium to aluminum creates alloys that are stronger and more resistant to corrosion than regular aluminum. These scandium aluminum alloys were used in some Soviet military aircraft and are now found in high-performance bicycles and sports equipment. The element is relatively rare and expensive, limiting its widespread use in everyday applications. Scandium was predicted by Mendeleev before it was discovered because he noticed a gap in his periodic table. The element was finally discovered in 1879 in Scandinavian minerals, giving it its name. Scandium has some interesting properties that place it at the boundary between light metals and transition metals. Research continues into potential new uses for scandium in fuel cells, lighting, and other technologies. This rare element adds strength where weight must be minimized, enabling performance at the edges of possibility. Yttrium is found in superconducting materials and LED lights that illuminate modern life efficiently. Some yttrium compounds become superconductors at relatively high temperatures compared to other superconducting materials. These superconductors carry electricity without resistance, though they still require cooling to work. Yttrium is also used in phosphors that convert electricity into light in LED displays and fluorescent lamps. The element strengthens certain aluminum and magnesium alloys used in aerospace applications. Yttrium was discovered in 1787 in a Swedish quarry that also yielded several other rare earth elements. The village of Ytterby gave its name to yttrium and 3 other elements discovered in minerals from that location. Yttrium oxide is used in camera lenses and other optical applications because of its high refractive index. This element helps conduct electricity without loss and converts energy into the light that illuminates screens and homes. Zirconium oxide is used as a diamond substitute in jewelry and in nuclear fuel rods that generate power. Cubic zirconia looks remarkably like diamond and is much less expensive, making it popular for jewelry. The material has a high refractive index that gives it brilliance and fire similar to genuine diamonds. Zirconium metal is used to clad nuclear fuel rods because it is strong, corrosion resistant, and transparent to neutrons. This allows neutrons to reach the fuel inside while protecting it from the hot, corrosive water cooling the reactor. Zirconium was discovered in 1789 and named after the mineral zircon from which it was isolated. The element is also used in some ceramics, surgical implants, and industrial applications. Zirconium's combination of beauty and nuclear utility shows how the same element serves both adornment and energy production. This element creates imitation diamonds while containing the power of the atom. Rhenium is one of the rarest elements on Earth and has the 3rd highest melting point of all elements. Only about 50 tons of rhenium are produced globally each year, making it extremely expensive. The element is used in superalloys for jet engine turbine blades that must withstand extreme temperatures and stresses. Rhenium improves the high temperature strength and durability of these alloys, allowing engines to run hotter and more efficiently. The element is also used in catalysts for petroleum refining and in some specialized thermocouples for measuring high temperatures. Rhenium was one of the last naturally occurring stable elements to be discovered in 1925. The name comes from Rhenus, the Latin name for the Rhine River near where it was discovered. Despite its rarity, rhenium plays crucial roles in aviation and industrial chemistry. This rare metal enables jet engines to push the boundaries of temperature and performance. Osmium is the densest naturally occurring element at twice the density of lead. A cubic centimeter of osmium weighs more than 22 grams, making it feel incredibly heavy for its size. This extreme density comes from osmium atoms being packed tightly together with minimal empty space. The element is very hard and brittle, making it difficult to work with or fabricate into useful shapes. Osmium is found in platinum ores and is sometimes alloyed with platinum and iridium for specialized applications. The element was discovered in 1803 and named after the Greek word osmi, meaning smell, because of the strong odor of its oxide. Osmium tetroxide is toxic and has a sharp, unpleasant smell that warns of its presence. Some fountain pen nibs and other precision instruments use osmium alloys for their hardness and wear resistance. This densest element represents matter packed as tightly as nature allows in stable form. Iridium is extremely rare on Earth, but is abundant in the layer of sediment deposited when an asteroid killed the dinosaurs. Scientists discovered an unusually high concentration of iridium in rock layers dating to 66 million years ago. This iridium spike appears worldwide at exactly the boundary between the Cretaceous and Paleogene periods. The discovery provided key evidence that an asteroid impact caused the mass extinction that ended the age of dinosaurs. Iridium is common in asteroids and meteorites, but rare on Earth because most of it sank to the core when the planet was molten. The element is extremely resistant to corrosion and is used in spark plugs, electrodes, and crucibles for growing special crystals. Iridium-platinum alloys are used for some of the standard weights that define the kilogram. The element serves as a cosmic marker in the rock record, forever marking one of Earth's greatest catastrophes. This rare metal connects falling stars to falling dynasties. Platinum is so unreactive it can sit in aqua regia, acid, longer than gold before dissolving. This noble metal resists corrosion and chemical attack better than almost any other element. Platinum does not tarnish, rust, or deteriorate under normal conditions, maintaining its appearance indefinitely. The element is used in catalytic converters that reduce harmful emissions from vehicle exhaust systems. Platinum is also used in jewelry, electronics, laboratory equipment, and as a catalyst for numerous chemical reactions. The metal is rarer than gold and has been valued throughout history for its beauty and useful properties. Platinum electrodes are used in fuel cells that may power future vehicles with only water as exhaust. The element was known to ancient civilizations in South America who mixed it with gold in metalwork. This noble metal represents permanence and purity, refusing to succumb to the chemical forces that corrode other materials. Palladium can absorb hydrogen gas at 900 times its own volume at room temperature. This remarkable property allows palladium to soak up hydrogen like a sponge absorbs water. The hydrogen atoms fit into spaces between palladium atoms in the metal's crystal structure. This ability makes palladium valuable for purifying hydrogen gas and for storing hydrogen in fuel cells. Palladium is used extensively in catalytic converters, where it helps convert toxic exhaust gases into less harmful substances. The metal is also used in electronics, dentistry, and jewelry, often as a white gold alternative. Palladium is rarer than platinum, and its price can exceed that of gold depending on supply and demand. The element is found in platinum ores and in some copper and nickel deposits. This hydrogen-absorbing metal plays crucial roles in cleaning air and enabling future hydrogen-based energy systems. Rhodium is the most expensive precious metal and is used in catalytic converters to reduce nitrogen oxide emissions. This extremely rare silvery white metal can cost many times more than gold or platinum. Rhodium is highly reflective and does not tarnish, making it useful for coating mirrors and jewelry. The element is primarily used in vehicle catalytic converters, where it converts nitrogen oxides into harmless nitrogen and oxygen. Without rhodium catalysts, cars would emit far more pollution that contributes to smog and acid rain. Rhodium is also used in some specialized laboratory equipment and in the production of LCD displays. The element is so rare that only about 30 tons are produced globally each year. Most rhodium comes as a byproduct of platinum and nickel mining in just a few countries. This expensive metal quietly cleans the exhaust of millions of vehicles while remaining largely unknown to the public. Silver is the best conductor of electricity and heat among all elements. This exceptional conductivity makes silver valuable for electrical contacts, switches, and high-performance wiring. Silver does not corrode easily in air, but tarnishes when exposed to sulfur compounds, forming black silver sulfide. The metal has been used for coins and jewelry for thousands of years because of its beauty and malleability. Silver has antibacterial properties and was used in wound dressings and water purification before modern antibiotics. Silver iodide is used in cloud seeding to encourage rain by providing particles for water droplets to form around. The element is also used in photography, mirrors, and solar panels, where its reflectivity and conductivity are valuable. Silver's combination of beauty and utility has made it precious to humans throughout history. This conductive metal moves electricity and heat better than any other element, while also protecting against bacterial growth. Tin has multiple solid forms and transforms between them with temperature changes in a phenomenon called tin pest. At temperatures below 13 degrees Celsius, tin slowly converts from its normal metallic form to a brittle gray powder. This transformation happens because the crystal structure of tin atoms rearranges into a different pattern. In cold climates, this tin pest can cause buttons, utensils, and other tin objects to crumble into powder over time. Tin is used extensively in solder for joining electrical components because of its low melting point and good electrical conductivity. The metal is also used to coat steel cans to prevent corrosion and contamination of food. Bronze, one of humanity's first alloys, is made from copper and tin and gave its name to an entire age of human history. Tin compounds are used in some plastics as stabilizers and in glass to make it more transparent. This ancient metal continues to serve modern technology while exhibiting strange transformations in the cold. The lanthanide series elements all have similar chemistry because electrons fill inner shells rather than outer shells. This unusual electron arrangement makes all 15 lanthanides behave similarly in chemical reactions. The elements are difficult to separate from each other because their similar properties mean they form similar compounds. Scientists in the 19th and early 20th centuries struggled for decades to purify individual lanthanide elements. Lanthanides are used in powerful magnets, phosphors for displays, catalysts, and numerous high-technology applications. Despite being called rare earths, most lanthanides are more abundant than gold or platinum. The name rare earth comes from the difficulty of separating these elements from their ores and from each other. Each lanthanide has unique properties that make it valuable for specific applications despite their overall similarity. These elements form a chemical family where siblings are so similar that telling them apart requires sophisticated techniques. Actinides are all radioactive, and most exist only in trace amounts in nature or must be created artificially. This series includes uranium and thorium, which are found naturally, and synthetic elements like plutonium and americium. All actinides have unstable nuclei that decay over time, releasing radiation and transforming into other elements. The heavier actinides are so unstable they exist only briefly in laboratories before decaying. Uranium and plutonium are used as nuclear fuel and in nuclear weapons because of their ability to sustain chain reactions. Americium-241 is used in smoke detectors where its radioactivity ionizes air, allowing the detector to sense smoke particles. Some actinides like curium and californium are used as neutron sources for research and industrial applications. These radioactive elements represent the heavy end of the periodic table where nuclear instability dominates. The actinides show us the limits of nuclear stability and the boundary between natural and human-made elements. Some elements, like technetium and promethium, have no stable isotopes at all and exist only temporarily. Every atom of these elements is radioactive and will eventually decay into other elements. Technetium is the lightest element with this property, and all its isotopes have half-lives much shorter than the age of Earth. Any technetium that existed when Earth formed has long since decayed away completely. Promethium is another element with no stable isotopes, existing only in trace amounts from uranium decay or created artificially. These elements appear in the periodic table as entries that have no permanent representatives on Earth. Stars produce technetium and promethium through nuclear reactions, but they decay before reaching our planet. Scientists create these elements in laboratories and nuclear reactors for research and specialized applications. These temporary elements remind us that not all matter is permanent, and some entries in the periodic table are more like fleeting visitors. Elements beyond uranium in the periodic table were all created artificially in laboratories through nuclear reactions. These synthetic elements do not occur naturally on Earth because they are too unstable and decay too quickly. Scientists create them by bombarding lighter elements with particles in accelerators, forcing nuclei to merge and form heavier elements. Neptunium and plutonium were the first synthetic elements created, discovered in the 1940s during nuclear research. Elements like americium, curium, berkelium, and californium followed as scientists learned to create ever heavier atoms. These synthetic elements have found uses in smoke detectors, spacecraft power sources, and scientific research. Creating new elements requires tremendous energy and sophisticated equipment that can manipulate individual atoms. Each new element exists only briefly before decaying, sometimes lasting only fractions of a second. These human-made elements extend the periodic table beyond what nature provides on Earth. Superheavy elements like oganesson exist for only fractions of a second before decaying into lighter elements. These elements at the far end of the periodic table are so unstable that only a few atoms have ever been created. Oganesson, element 118, was created by smashing calcium atoms into californium atoms at high energy. The resulting oganesson atoms existed for less than a millisecond before decaying. Scientists study these fleeting elements to understand nuclear physics and test theories about how protons and neutrons behave in heavy nuclei. Creating even a single atom of a superheavy element can take months or years of continuous experiments. These elements have no practical applications and exist purely for expanding human knowledge. Each new superheavy element pushes the boundary of how large an atomic nucleus can become before instability tears it apart. These temporary elements represent the frontier of human ability to manipulate matter at its most fundamental level. The island of stability predicts that some superheavy elements might be more stable than their neighbors. Nuclear theory suggests that certain combinations of protons and neutrons create extra stability even in very heavy nuclei. Elements near this predicted island might exist for seconds, hours, or even longer instead of microseconds. Scientists are searching for these potentially more stable superheavy elements by creating atoms with the right number of protons and neutrons. If the island of stability exists, it could reveal new physics and possibly even elements with unexpected properties or uses. The search continues as laboratories around the world attempt to create heavier and heavier elements. Each new element discovered provides clues about whether the island of stability is real or just a theoretical possibility. This quest represents humanity's desire to explore the unknown and map the limits of possible matter. The island of stability may hold elements unlike anything currently known, waiting to be discovered in the vast, unexplored territory of super-heavy nuclei. Elements are continuously recycled through stellar life cycles over billions of years across the universe. Stars form from clouds of gas and dust that contain elements from previous generations of stars. These new stars fuse lighter elements into heavier ones throughout their lifetimes. When stars die, they release their enriched material back into space through stellar winds or explosive supernovae. This material mixes with existing gas clouds and eventually collapses to form new stars and planets. Each cycle enriches the universe with heavier elements, slowly increasing their abundance over cosmic time. The Sun and Earth formed from material that had already been through several stellar generations. Every atom in your body has been recycled through multiple stars over billions of years. This cosmic recycling connects the past, present, and future of matter in an endless cycle of creation and destruction. Each generation of stars creates heavier elements that enrich the next generation in a process of gradual cosmic enrichment. The first stars formed from pure hydrogen and helium left over from the Big Bang. These primordial stars created the first carbon, oxygen, and other light elements through fusion. When these stars died, they scattered their newly created elements into space. The next generation of stars formed from gas, enriched with these heavier elements, and created even more. This process has continued for over 13 billion years, building up the diversity of elements. Later generations of stars like the Sun contain much higher percentages of heavy elements than the earliest stars. The universe has been building complexity slowly, generation by generation, through the lives and deaths of countless stars. This enrichment process made planets like Earth possible, with their rich variety of elements supporting life. The solar system formed from gas enriched by previous generations of stars that died before the Sun was born. About 4.5 billion years ago, a cloud of gas and dust began to collapse under its own gravity. This cloud contained hydrogen and helium from the Big Bang plus heavier elements from ancient supernovae and stellar winds. The collapse formed the Sun at the center, with planets forming from the leftover disk of material. Earth and the other rocky planets formed from the heavier elements that could condense into solid particles. Without the element enrichment from previous stellar generations, rocky planets could not have formed. The diversity of elements in the solar system reflects the long history of nucleosynthesis in earlier stars. We live in a second or third generation solar system built from the ashes of long-dead stars. Every element heavier than helium in the solar system came from stars that lived and died before our Sun existed. Elements in your body have been recycled through multiple stars over cosmic time before arriving in you. The carbon, nitrogen, and oxygen in your cells were created in stellar cores billions of years ago. These atoms drifted through space for eons after being released by dying stars. They became part of the gas cloud that formed the solar system and eventually Earth. Through geological and biological processes, these atoms entered plants, animals, and eventually your body. The atoms in your body have been part of countless other organisms throughout Earth's history. After you die, these atoms will return to the environment and become part of other living things. On even longer timescales, they may leave Earth and eventually be incorporated into new stars. Your atoms are ancient travelers passing through you on a cosmic journey that spans billions of years. The ratio of different isotopes in elements reveals their cosmic origin stories and the processes that created them. Isotopes are versions of the same element with different numbers of neutrons in their nuclei. Different nuclear processes produce different isotope ratios that serve as fingerprints of their origin. Scientists can determine whether elements formed in supernovae, neutron star collisions, or stellar cores by examining isotope ratios. Some meteorites contain grains with isotope ratios that are completely different from anything else in the solar system. These presolar grains formed in specific ancient stars before the solar system existed and were incorporated into meteorites. By studying these grains, scientists can learn about individual stars that existed before the Sun. Isotope ratios connect laboratory measurements to cosmic events billions of years ago and light years away. These chemical signatures tell stories about where and how elements were created. Red giant stars create carbon and oxygen through helium fusion in their cores during their final stages of life. When a star like the Sun exhausts its hydrogen fuel, it expands into a red giant. The core contracts and heats up enough for helium atoms to fuse together. 3 helium nuclei combine to form carbon through the triple alpha process. Some carbon nuclei then capture additional helium to form oxygen. This process enriches the star with carbon and oxygen that eventually spreads into space. Red giants blow off their outer layers in gentle stellar winds that carry these elements across the galaxy. Planetary nebulae are the beautiful remnants of this process, glowing clouds enriched with carbon and oxygen. Without red giants, the universe would have far less carbon and oxygen, making life as we know it impossible. These dying stars are the main factories for the elements that form the basis of organic chemistry. White dwarf stars accumulate heavy elements on their surfaces from companion stars in binary systems. When a white dwarf has a companion star nearby, it can pull material from that star through gravity. This stolen material falls onto the white dwarf's surface, accumulating over time. If enough material accumulates, the white dwarf can explode in a thermonuclear reaction called a Type Ia supernova. These explosions are incredibly bright and produce large amounts of iron and other intermediate mass elements. Type Ia supernovae are so consistent in brightness that astronomers use them as standard candles to measure cosmic distances. The elements created in these explosions scatter through space and enrich future generations of stars. White dwarfs are stellar remnants that can still participate in element creation through violent explosions. These compact stars play a crucial role in producing the iron that makes up Earth's core and much of its rocks. Neutron star collisions produce rapid neutron capture, creating the heaviest elements like gold and platinum. When 2 neutron stars spiral into each other, they merge in an incredibly violent collision. The extreme conditions create a flood of neutrons that are rapidly captured by atomic nuclei. In just seconds, this rapid neutron capture builds up the heaviest stable elements in the universe. Gold, platinum, uranium, and many other heavy elements are primarily created this way. These collisions also produce gravitational waves that can be detected by sensitive instruments on Earth. In 2017, scientists observed both gravitational waves and light from a neutron star merger for the first time. This observation confirmed that neutron star collisions are indeed the main source of heavy elements. The gold in wedding rings and the uranium in nuclear reactors all came from these rare but powerful cosmic events. Cosmic rays hitting Earth's atmosphere create trace amounts of unusual isotopes continuously throughout time. Cosmic rays are high-energy particles from space that constantly bombard Earth. When these particles hit atoms in the upper atmosphere, they can split nuclei or create new isotopes. Carbon-14, used for radiocarbon dating, is continuously created this way when cosmic rays hit nitrogen atoms. Other rare isotopes like beryllium-10 and chlorine-36 are also produced by cosmic ray interactions. These cosmogenic isotopes provide valuable information for dating geological samples and studying atmospheric processes. The production rate varies with solar activity and Earth's magnetic field strength over time. Scientists use cosmogenic isotopes in ice cores and sediments to reconstruct past climate and solar activity. This ongoing nuclear reaction in the atmosphere connects cosmic events to earthly processes and scientific dating methods. The abundance of elements in the universe follows a general pattern of decreasing with increasing atomic number. Hydrogen and helium are by far the most abundant elements, making up over 99% of normal matter. As atomic number increases, elements generally become less abundant because they require more energy to create. There are notable peaks in abundance for elements like carbon, oxygen, and iron that are efficiently produced in stars. Elements heavier than iron drop off sharply in abundance because they can only form in supernova and other rare events. This abundance pattern reflects the nuclear processes that create elements and how much energy each process requires. The rarest stable elements are those that are difficult to produce and easily destroyed in stellar environments. Understanding element abundance helps scientists learn about the universe's history and the processes within stars. This cosmic pattern shows that what is common in the universe is determined by the physics of nuclear fusion. Elements with even atomic numbers are generally more abundant than neighboring odd-numbered ones throughout the universe. This pattern appears because fusion processes in stars tend to build up even-numbered elements more efficiently. Helium contains 2 protons, carbon has 6, oxygen has 8, and these are all very abundant elements. The pairing of protons and neutrons in even-numbered nuclei creates extra stability that makes these elements easier to form and harder to destroy. Odd-numbered elements like nitrogen, fluorine, and sodium are less abundant than their even-numbered neighbors. This alternating pattern of abundance is visible throughout the periodic table up to the heaviest elements. The pattern reflects fundamental nuclear physics and the way particles pair together for stability. Scientists can predict the approximate abundance of elements just by knowing whether they have even or odd atomic numbers. This cosmic pattern shows how nuclear structure determines what exists in the universe and in what quantities. The universe will continue creating heavier elements until all stars eventually die in the far distant future. Stars are still forming today from gas clouds enriched by previous stellar generations. Each new star will create more heavy elements through fusion and release them when it dies. Over trillions of years, the percentage of heavy elements in the universe will slowly increase. Eventually, all the hydrogen fuel will be used up and star formation will cease. The last stars will die, leaving behind only cold remnants like black holes, neutron stars, and white dwarfs. After that point, No new elements will be created naturally, though existing atoms will persist. The universe will enter a dark era where element creation has ended and only decay continues. This distant future marks the end of the cosmic element building process that began with the Big Bang. For now, though, the universe is still in its element creating phase, slowly building complexity. Some meteorites contain presolar grains with isotope ratios, showing their formation in specific ancient stars. These microscopic mineral grains are older than the solar system itself. They formed in the atmospheres of dying stars billions of years ago and somehow survived incorporation into meteorites. The isotope ratios in these grains are completely different from everything else in the solar system. Scientists can match these signatures to theoretical models of different types of stars. Some grains came from red giants, others from supernovae, and still others from unusual stellar environments. Each grain is a time capsule preserving information about an individual star that died before the sun was born. By studying thousands of these grains, scientists learn about the variety of stars that contributed material to the solar system. These ancient fragments connect laboratory microscopes to stars that shone billions of years ago in distant parts of the galaxy. Elements bond together following patterns based on electron shells and the octet rule. Atoms are most stable when their outermost electron shell is full, typically containing 8 electrons. Atoms with partially filled outer shells will share, gain, or lose electrons to achieve this stable configuration. This drive toward stability determines how elements combine to form molecules and compounds. Sodium has 1 electron in its outer shell and readily gives it away, while chlorine needs 1 electron to complete its outer shell. When sodium and chlorine meet, sodium donates its electron to chlorine, and they bond together, forming table salt. Carbon has 4 electrons in its outer shell and can form 4 bonds to fill it with 8. This bonding flexibility allows carbon to create the millions of organic compounds that make life possible. The octet rule explains why some elements bond readily while others remain chemically inert. The periodic table organizes elements by repeating patterns of chemical behavior discovered through centuries of study. Elements in the same column behave similarly because they have the same number of electrons in their outer shell. The vertical columns are called groups or families because elements in them act like chemical relatives. Mendeleev organized the first periodic table in 1869 by arranging elements by atomic weight and chemical properties. He left gaps where he predicted undiscovered elements should be, and he was proven right when those elements were found. The modern periodic table arranges elements by atomic number rather than atomic weight. This organization reveals the underlying structure of matter and helps predict how elements will behave. The periodic table is one of the most useful tools in science, encoding vast amounts of information in a simple visual format. It shows that apparent chemical complexity arises from simple patterns of electron arrangement. Elements in the same column share similar properties due to identical outer electron configurations repeated down the group. The leftmost column contains alkali metals like lithium, sodium, and potassium that all have 1 electron in their outer shell. All these metals are soft, reactive, and form compounds with similar formulas and properties. The rightmost column contains noble gases like helium, neon, and argon that all have full outer electron shells. These gases are unreactive because their electron shells are already complete and stable. Elements in the middle columns show gradations of properties but still share family characteristics. The column containing fluorine, chlorine, bromine, and iodine are all reactive nonmetals that form similar compounds. This vertical repetition of properties reveals that chemical behavior depends mainly on outer electrons. The periodic table turns chaos into order by showing that elements follow predictable family patterns. Metallic elements dominate the left and center of the periodic table, making up most of the known elements. About 3/4 of all elements are classified as metals based on their properties. Metals typically conduct electricity and heat well, have a shiny appearance, and can be shaped without breaking. They tend to lose electrons in chemical reactions, forming positive ions. The transition metals in the center of the table include iron, copper, gold, and many elements essential to technology. Metals become progressively less reactive as you move from left to right across each row. The most reactive metals are on the far left, like sodium and potassium, which react violently with water. Metals form the structural foundation of modern civilization in steel buildings, copper wires, and countless alloys. This predominance of metals shows that most elements share similar fundamental properties based on their electron structures. Noble gases in the rightmost column are stable because they have complete electron shells requiring no changes. Helium has 2 electrons filling its only shell, while the others have 8 electrons filling their outer shell. This completeness means noble gases have no tendency to gain, lose, or share electrons with other atoms. They exist as single atoms rather than molecules, drifting through space or air without reacting. For many years, scientists thought noble gases could not form compounds at all. In the 1960s, chemists finally created xenon and krypton compounds under extreme conditions. Even so, noble gases remain the most unreactive elements and serve as standards of chemical stability. Their presence in the periodic table marks the endpoints where electron shells are completely filled. These stable elements show that atoms seek completeness and react only when their electron shells are incomplete. Elements can exist in different oxidation states by losing or gaining electrons in chemical reactions. The oxidation state indicates how many electrons an element has lost or gained compared to its neutral state. Some elements have only one common oxidation state, while others can exist in many different states. Iron can be in the PS2 state in some compounds and +3 state in others, giving different properties. Chlorine can have oxidation states ranging from 1 to +7, depending on what it bonds with. These different states allow elements to participate in a wide variety of chemical reactions. Oxidation states determine the formulas of compounds and how elements interact with each other. Understanding oxidation states is essential for predicting chemical behavior and balancing equations. This flexibility in electron arrangement allows the same element to play different roles in different chemical environments. The diversity of matter comes from just over 100 elements, combining in countless ways throughout nature and technology. Every substance in existence is made from combinations of these fundamental building blocks. Water combines hydrogen and oxygen. Sugar combines carbon, hydrogen, and oxygen in specific ratios. The millions of known compounds demonstrate the extraordinary variety possible from simple elements. Chemical bonds arrange atoms in different patterns, creating substances with completely different properties. Diamond and graphite are both pure carbon, but have different structures giving them opposite characteristics. Living things create the complexity of life using mainly carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Technology harnesses element combinations to create plastics, medicines, semiconductors, and materials unknown in nature. This shows that complexity and diversity emerge not from exotic ingredients, but from how simple elements connect and arrange themselves into larger structures.